In the last video, I discussed about velocity and acceleration. I'll talk more on acceleration. When do you say the body is undergoing accelerated motion? When the velocity of a body changes with time, then we say it is accelerated. Then we say when the velocity of the body changes with time. And in last video we saw that velocity can change in two ways. Either its magnitude change with time, or its direction can change with time, or you can have both magnitude and direction both change with time. Then we say the body is undergoing accelerated motion. The body is undergoing accelerated motion. Right? So when the velocity changes with time, we say the body is undergoing accelerated motion. And mathematically we define acceleration as rate of change of velocity with respect to time. That's called acceleration. So A is dv by dt. So A can remain constant, or it can also change with time. The acceleration of body can remain constant, or see, if V is changing with time, we say it is accelerated motion. But this acceleration may also change with time, or acceleration can remain constant. If acceleration remain constant means, if suppose A is 2 meter per second square, that means, see, regarding unit, you must be very clear that the unit of distance is meter, and velocity is dr by dt. So it is distance upon time. Dimensionally, this is distance upon time, dimension wise. So it is meter per second, and acceleration is dv by dt. So it is meter per second, or we call it meter per second square. So when acceleration is 2 meter per second square, what does it mean? It means that the velocity is increasing at the rate of 2 meter per second per second. When acceleration is 2 meter per second, that means the velocity increases at the rate of, suppose the magnitude of acceleration is 2 meter per second, then that means velocity increases at the rate of 2 meter per second per second. That means if right now velocity is 10 meter per second, then in next 1 second it will go to 12 meter per second, and next 1 second is going to be 14 meter per second. So we say the body is accelerating at the rate of 2 meter per second square. This velocity is increasing every second by 2 meter per second square. If it is 10 meter per second right now, then after 1 second it is going to be 12 meter per second, and next second it will be going to 14 meter per second. After 3 seconds it is going to be 16 meter per second, right? So in this way velocity is increasing. That means at t equal to 10 second, if the velocity is say 10 meter per second, and at 12 second velocity is going to be 12 meter per second. At 11 meter per second, the velocity is going to be 12 meter per second. At 12 second, the velocity is going to be 14 meter per second. So every second passes on, the velocity increases by 2 meter per second. So the acceleration is 2 meter per second per second. It's increasing at the rate of 2 meter per second per second, right? That's what it means. That's what it means. And sometimes this acceleration can also be varying. This can also be time varying. I'll give you an example. See, many of you might be riding a bike or two-wheeler, right? When you ride two-wheeler, when you start your two-wheeler, initially your velocity increases rapidly. But as the time passes on, the rate of increase of velocity decreases. Rate of increase of velocity decreases does not mean velocity decreases. Velocity still increases, but increase at lower pace. Initially, when you start your vehicle, right? So initially you accelerate faster, means your velocity increases rapidly. Velocity increases rapidly. Velocity increases at a rapid rate. But as the time passes on, your acceleration falls. Acceleration falls means velocity still increases, but it is increasing at less rate. It is increasing at decreasing pace, right? Velocity still increases, but it is increasing at less rate or decreasing pace. So we say acceleration falls. Acceleration falls, right? And acceleration constant means your velocity increases at constant pace throughout. Then you say it is constant acceleration. So your acceleration can be time varying, it can be constant. It can be constant. If your acceleration is constant, then we say if acceleration is constant, then we say it is uniformly accelerated motion. We say it is uniformly accelerated motion, right? And this motion can be, it can be in a straight line. If it is in a straight line, then we say it is one-dimensional motion. We say it is one-dimensional motion. And if it is not in a straight line, if it is in a, see, there are three kind of motion you can have. Motion can be one-dimensional, that is, motion in a straight line is called one-dimensional motion. Also in a straight line, STRA, that's called one-dimensional motion. And if you have motion in a curve which is confined to, say here even straight line is also called curve, but I am talking about a curve different from straight line, a curve which is not the straight line. If a motion is in a curve which is different from straight line, which is, and this curve is confined to plane, say if it is moving a curve, say straight line means if it is moving like this, then we say it's one-dimensional motion. If body is moving like this and this curve is confined to a single plane, then it's a two-dimensional motion. And if it is moving in a curve such that this curve is not confined to a plane, this curve, the plane of curve, the curve is not lying in a single plane, then we say it is three-dimensional motion. For example, if suppose this is three-dimensional coordinate system, and if suppose the body moves in this kind of circle, it's not confined to sorry, this is, can we say the body moves like this, so this curve is not confined to a single plane, so it is a three-dimensional motion. All the coordinates, see, you need three coordinates, and if all the coordinates change with time, all the coordinates during the motion, if all these three coordinates changes, we say it is three-dimensional motion. Here what do you have? You can take a coordinate system like this, x and y. This plane can itself be taken as xy plane, and then you see only x and y coordinate change with time. Your z coordinate remain constant. Here I can take even this as x-axis. So what do you have? Your only one coordinate is changing with time. Only x coordinate changing with time. And taking this coordinate system is our discretion. So if only two coordinates changing with time, it's a two-dimensional motion. Here only one coordinate changing with time, it's one-dimensional motion. Here all the three coordinates are changing with time, it's called three-dimensional motion. It's called three-dimensional motion. That's what we mean when we say one-dimensional, two-dimensional, or three-dimensional motion, right? Get your point? Moreover, somebody can say that I'll take my coordinate system like this. and then here all the three coordinates are changing with time, right? So but it's not a three-dimensional motion. Even if we take this coordinate system, it's not a three-dimensional motion. It's not a three-dimensional motion. If there is a possibility that you take a coordinate system where only one coordinate are changing with time, it's one-dimensional motion. There is always a possibility to take this as x-axis, this as y-axis, this as z-axis, and while the body moves, only one coordinate changing with time. So if there is a possibility to choose a coordinate system such that while the body moves, only one coordinate changing with time, then it is one-dimensional motion. Here there is a possibility when a body is moving in a curved path which is confined to a plane, there is always a possibility to choose a coordinate system. See, choosing a coordinate system is our discretion, it's our freedom. No law of nature, none of the laws of nature tells you anything regarding coordinate system. You don't have any law of nature hinting you about taking this or that coordinate system. So if body is moving a curve and that curve is confined to a plane, there is always a possibility of choosing a coordinate system such that while body moves on that curve, only two coordinates changes, and in that case we say it is two-dimensional motion. While you see this case, while the body moves in this curve, then in every, I cannot take a coordinate system where only one or two coordinates changing with time. In every case, all the three coordinates are changing with time. It's not a curve confined to a plane, so it's a three-dimensional motion. Three-dimensional motion. Okay, that's something which we will be requiring quite often. So let's come back to what is called uniformly accelerated motion. When the body is undergoing uniform acceleration, uniform acceleration means acceleration remaining constant with time. When acceleration remains constant with time, we call it uniform acceleration, and the motion is called uniformly accelerated motion, right? So if A remains constant with time, this A is what? A is dv by dt, and this is constant. See, acceleration is vector quantity, and when vector quantity is constant, that simply means its magnitude is constant, its direction is remaining constant. Its direction is remaining constant with time, its magnitude remains constant with time. Then only I say acceleration is constant. The vector quantity is said to be constant only when its magnitude and direction both are constant, right? So since this is a constant quantity, I can write this as, see, you must have introductory knowledge of calculus when you read this topic. If you don't have, you just go through some part of calculus, initial chapter of calculus, then only you will be feeling good at this chapter. So I can write this dv as a dt, and then I can integrate it. Then I can integrate it, and integrating this will give me v equals to, since a is constant, plus some constant, whenever you carry out indefinite integral, when you integrate it, you have to add one constant, right? And why you are doing this, you will be understanding it well while you read this chapter of indefinite integral. See, you must read this chapter of indefinite integral at least. If you don't read a definite integral, then also it will be okay. If you read definite integral, it's good, it's fine, but I will try my best to use definite integral less and use this basic theorems of integral calculus, indefinite integral. And you must also read some part of differentiation. You don't need a very good concept of the chapter for this physics part, but you need very good concept of this topic when you do mathematics, right? But for just use in physics, you don't need a very strong concept of calculus, right? Later on at higher level, when you read physics, you need a very strong concept of calculus, but right now you can just remember the formula, that will be useful to you, right? So dv is a dt. A, why I have taken a outside integral? Because a is constant with time, so that will be at plus c. And in order to evaluate this constant, you must know the velocity at time t equal to 0. we must know what is the velocity at t equal to 0. So suppose at t equal to 0 the velocity is v naught. So if I put this at t equal to 0, the velocity is v naught. So you just put t equal to 0 over here. So putting this in this equation, what you get? You get c equals to v naught. C can be a vector constant. So this v is v naught plus at, right? V is v naught plus at. And what is v? V can be expressed in terms of position as dr by dt. Get your point? So you have dr by dt as this. So even this can be written as and now I can integrate it on both sides. So again you have a constant. So your r vector is v naught t. You remember, I'll just write down the formula. You have the formula xn dx. This is the formula where n has to be n should not be equal to 1, minus 1, sorry. N should not be equal to minus 1. If n equals to minus 1, then this is, in that case, it will be dx by x, and the formula for this is log x plus c. Just remember this formula. I'll keep on writing the formula, right, for your reference. So since you have t, so t dt, so t to the power, this is t to the power 1 dt. So t 1 plus 1, 1 plus 1, so t square by 2 plus some vector constant. See, the constant has to be vector. Why? Because you cannot add a scalar to a vector. You cannot add only vector to a vector. See, scalar cannot be added. The addition of a vector and a scalar is not defined operation, right? So if you are given at t equal to 0, r is r naught. So if you put it over here, you get c as r naught vector. So your r gives you, the position is given by r naught plus v naught t plus this. So this is equation, this is your equation of motion. And now if the body is confined to one dimension, the body is moving in one dimension, then this formula will be, I can take the coordinate system as, I can take this coordinate system. See, choosing coordinate system is our freedom. So if I am knowing that the body is moving along this straight line, then I can take one of my axes along that straight line itself. So here you see only x coordinate is changing with time. So at any point, if the body is lying at a distance of x from the origin, then its position vector would be given by what? The position vector would be given by xi cap. And since the body is moving in a straight line, suppose the acceleration is say ai cap, the velocity is say vi cap, everything is lying in a straight line, right? So this equation will turn to what? It would be x equal to x naught. Let's put it over here. This will give you what? Xi cap equals to x naught I cap plus v naught I cap t ai cap t square, and everywhere you have I cap, so we can equate the coefficient of I cap, so we get x equal to x naught plus v naught t is half a t square. And if body lies at x equal to 0, at t equal to 0, so in that case, suppose the body is at origin at t equal to 0, then that means x naught is 0 at t equal to 0. Then your position is just given by this x equals to v naught t plus half a t square. Get a point? Similarly, v is v naught plus at, where v naught is the initial velocity. V naught is the initial velocity. This is how v varying with time. This is now how v vary with time. Getting a point? Okay. So this is a distance traveled by the time t. This is distance traveled by at the end of time t. After time t, the distance traveled is x. At t equal to 0, x was 0. X was 0. So after time t, the distance traveled is this, right? And we can write x in terms of v also. See, from here you get what? T equals to v minus v naught by a. So you can write it over here. V naught, what? I should write like this. V minus v naught by a plus half square by a square. So this will cancel out. So what is left? V naught minus v by a upon v naught plus this, or this is what? If I add it, this will be v naught plus v upon 2 a, or we can write it as v naught square a mistake. It's not v naught minus v, it's v minus v naught. That's why I was getting incorrect result. Oh, now it is now correct. So it is v minus v naught which will be taken out upon a, and v plus, so that will give me this is v naught, so this will be v minus v naught upon a, and this will be v plus v naught by 2, and that is v square v naught square 2a equal to x. So you can say v square is v naught square plus 2ax. Means final velocity square equals to initial velocity square plus 2x. I can get this formula easily. If suppose acceleration is a is the acceleration. If a is the acceleration, so a is dv by dx. Right, I can get this. This is a bit lengthy. I'll tell you in very short how this is coming. So dv by dt is a is acceleration. Suppose I am taking one dimensional case. See, this dv by dt can be written as dv by dx into dx by dt. Since in one dimensional motion, this dx by dt will be the velocity. So v dv by dx as a, and a is constant, uniformly accelerated motion. So this will come as v dv a dx, and now I can integrate it plus some constant. So v dv is again v square by 2, and this is ax plus some constant. Suppose at x equal to 0, suppose the body was at t equal to 0, body was at x equal to 0, suppose the velocity was v naught, then in that case you get what? C equals to v naught square by 2. You put these values, x equal to 0 over here and v equals to v naught over here, so you get C, and that leads to what? V square by 2 is equal to ax, or you can say v square is v naught square plus 2x. So you can get it in any way. You can get it from here also by eliminating t from these two equations, or you can get it from here. Any way you can do. point. So this is the basic equations of motions for one dimension. It's uniformly accelerated motion, and we'll make use of it in doing some questions.